Hello, this is Terry again. Today I want to share with you another how-to example, the Bernoulli numbers. You may or may not have heard of the Bernoulli numbers. They are an interesting sequence of rational numbers that are useful in solving a variety of problems. I will show you I'll give you basically a brief introduction of Bernoulli numbers here in this video, and in the next video I'll show you how to use the Bernoulli numbers to express the infinite series representation of various trig functions. The work in this video is based on these three references. Feel free to take a look at these. In particular, this last paper here by Orosi is an interesting approach, a very simple, straightforward, and very elegant approach to establishing the Faulhaber formula, which I will introduce you in a second. We'll walk through how Orosi proved this general formula. All right, as an introduction, let's imagine you're trying to add up the first n integers, each individually raised to some kth power, some natural number kth, like so 1 plus 2 plus dot 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 plus n, and then 1 square plus 2 square plus dot 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 plus n square. Basically, it's a sum of I to the kth power. I runs from 1 to n. Going forward, I'm going to use this notation s sub n k as a means of writing this long expression. Now, how do you establish this? Well, you can use various different rudimentary methods. For example, one method is to use the telescoping method. You can watch one of my videos, one of my previous videos. I show you how to use the telescoping method to establish, a formula for the general K. The problem with a lot of these rudimentary methods is it involves a lot of work. So for example, if you look at this telescoping method that I show you, right, you have to first establish the case for k equal to 1, and then use that, you establish the case for k equal to 2, and then the case equal to 3, and so on. You build it up. It's not bad. Once you figure it out once, I mean, you can just, write it down somewhere, memorize it, it's not bad, right? But it still involves a lot of work, a lot of algebraic work. Now, what would be nice or ideal is if there's a general formula that we can use. And it turns out that there is, right? But again, like I said, to me, you can use the formula or you can just build it up yourself. Either way. Anyway, so in 1631, Johann Faulhaber figured it out how to do this, but he did it to the best of my knowledge, he did it only for the first few odd values of k. It was in 1713 where Jacob Bernoulli looked at his work and noticed there's a pattern that you can lead to a general case. The general case of any general k value, k being a natural number, 1, 2, 3, 4, and so on. This general formula turned out to depend on a well-determined sequence of rational numbers that later was called the Bernoulli numbers, named after him. All right, so let's start with Johann Faulhaber's numbers. All right, so in 1631, Faulhaber, he published a formula for s of nk for the first few odd values of k. So for example, when k equal to 1, is the well-known 1 plus 2 plus dot dot plus n, which is n times n plus 1 over 2. Let's just call it m. Let's just call this answer m for a minute. Then he showed that when k is equal to 3, 1 cubed plus 2 cubed plus dot 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 plus n cubed, that's m squared. In other words, when k is equal to 3, Sn3 can be expressed in terms of Sn1. And in fact, when k is equal to 5, 1 to the 5th plus 2 to the 5th plus dot 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 plus n to the 5th is 4/3 m cubed minus 1/3 m squared, again expressed in terms of Sn1, right? And so on. So that's interesting. Because most people up to that point, right, when you're trying to sum 1 through n, you express it in terms of n. But he expressed everything in terms of the first answer. So basically, he figured out the first answer, and then he said, well, then k equal to 3 can be expressed as the first answer, and k equal to 5 is another function of the first answer, and so on. That's interesting. So you can work out this, right? You can using various rudimentary methods, you can work out a general case that's beyond, that includes the even value of k, so not just the odd value. Okay, so let's try out a few terms, right? So again, using whatever method you like, let's imagine you figure this out. By the way, instead, Actually, there's a typo here. This should be S sub n, not n minus 1. Yeah, this should be S sub n, not n minus 1, okay? So this is important. So these formula are written in terms of S sub n. So in S sub n, for example, when k is equal to 0, you're basically adding up 1, plus 1 plus 1 plus 1, right, and so on, n times. Of course, the answer is 1 over 1 times n. When k is equal to 1, is n times n plus 1 over 2, so it's 1/2 n squared plus 1/2 n, and so on. You can write all these out. So when you do this, right, so what happened was, in 1713, Jacob Bernoulli noticed something, there's a pattern in this. By the way, again, this is important, right? This is S sub n. The reason I got this confused is because Jacob Bernoulli actually looked at S sub n minus 1 instead. So what Jacob Bernoulli did was, instead of summing 1 plus 2 plus dot 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 plus n, he worked with 1 plus 2 plus dot 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 plus n minus 1. So only up to n minus 1. So if it's up to n minus 1, right, then you notice that, the above is going to be 1/2. Well, remember, when k is equal to 1, if you sum it only up to n minus 1, it's obviously going to be n minus 1 times n over 2. So this is the same as 1/2 n squared minus 2 times 1/2 n to the 1. And when k is equal to 2 is 1/3 n cubed minus 3 times 1/2 n squared plus 0 n. When k is equal to 3, you're going to get 1/4 n to the 4th minus 4 times 1/2 n cubed plus 6 times 1/6 n. All right, skipping 0 n squared, and so on. You begin to see a pattern here. Right? You notice, first of all, this outside is 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and so on. So whenever k here, you're going to get 1 over k plus 1. Right? Inside the first term, inside each parentheses, like the first term is always just n to the k plus 1. Right? So when k is 1 is n squared. When k is 2 is n cubed, and so on. And then over here, you notice this is the 2, 3, -2, -3, -4, -5, and so on. And so on. So, he began to notice some pattern here. So he said, if you write it like this, so for example here, right? So you 2, 3, 4, 5, 6, 7. Again, skip the sign, right? Ignore the sign for a minute. You see the pattern. This is 1, 1, 1, 1, 1, 1, 1. This is 2, 3, 4, 5, 6, 7. This is what? This is 0, 6, 10, 15, ignore 0, right? 6, 10, 15, 21. And then ignore the next one, and 5, 15, 35, and so on. So he began to realize that, hey, this has something to do with the Pascal triangle. So using combinatorial notation, you can rewrite this table as follows, right? This is 1/2, 2 chooses 0, minus 2 chooses 1, times something, 1/2 n. And then 3 chooses 0, minus 3 chooses 1 times 1/2 n squared, plus 3 chooses 2, 1/6 n, etc., etc., etc. Now, some places where you're going to get 0, you need to fill it in with the same combination, but except you fill it in with 0. So he already noticed something strange. Like somehow, if you do a lot of these, you begin to see a pattern that starting from this column, right? All these odd indices, right? It's going to all go to 0. So, for example, 4 chooses 3, 5 chooses 3, 6 chooses 3, 7 chooses 3, the third one, the fifth one, the seventh one, they all go to 0. So those are very interesting patterns. So to him, it seemed to him, right, that S sub n minus 1k, remember he summed it up to n minus 1. S sub n minus 1 to k looks like it's going to be 1 over k plus 1 times the sum, times the sum of k plus 1 chooses j, b sub j, some constant b sub j, times n to the k plus 1 minus j. So keeping in mind, this is important. When you sum up to n minus 1, the answer is in terms of n. So it's always 1 higher. And what are these constants? Well, again, just by looking at this table, it seemed to him b sub 0 is 1, b sub 1 is -1/2, b sub 2 is 1/6, b sub 3, b sub 5, and b sub 7, starting with 3, all the odd indices are 0, b sub 4 is -1/30, and then b sub 6 is 1/42, and so on and so on. So on and so forth. So that's what appeared to him, right? Well, it wasn't until 1755 when Leonard Euler started putting some math behind it. What he needed to do was he needed to establish a formula for the b sub k's. So he figured it out. He said, you know what? If you look at the function g of z defined as z over e to z minus 1, if you expand this function out around 0 through the Taylor series expansion, basically the Maclaurin series of this guy, can be written like this. And it's going to be written like this infinite series, k running from 0 to infinity, b sub k over k factorial, z to the k. Right? This is a classic expansion of Maclaurin series. All these coefficient b sub k, right, will fit exactly these guys. Okay, so now let's start. So we're gonna show you why this is the case, right? So notice first, g of z as defined here, z over e to the z minus 1, is analytic everywhere except at z equal to 0. You can't have z equal to 0 because e to the 0 is 1, 1 minus 1 is 0. You can't divide by 0. So this function is good everywhere except at z equal to 0. In fact, you can, if you take this expression and you keep differentiating it, you'll notice something. Every derivative, first derivative, second derivative, third derivative, etc. Every derivative is going to involve something divided by e to the z minus 1, which makes it undefined at z equals 0. And yet, in order for me to calculate all these b sub k's, I need to take these derivatives, and but to isolate b sub k, I need to take these derivatives and set z equal to 0. But I can't do that. Right? I cannot just evaluate it. So what I do? Well, it turns out if you cannot evaluate a function at 0, you can consider what happens to the limiting behavior of the function near 0, right? So it turns out that b sub k is the same as taking the limit of the derivative, the kth derivative of g, letting z go to 0. It's the same as that limit, okay? And so by comparison to the Taylor series, right, or Maclaurin series on 0, this guy, is clear that the kth derivative is just b sub k is just the kth derivative evaluated at 0. Okay, so when you take these whole bunch of these limit, you're going to begin to notice something. B sub 0 is 1, b sub 1 is negative half, and in a minute I'll show you how, right, and so on. And you also notice that all the j, when starting at 3, starting at 3, all b sub 3, b sub 5, b sub 7, all of them are 0. You can prove that. In a minute we'll show you exactly that. And then for the rest, you can evaluate and get these numbers. Okay, so let's actually prove that. Remember we said b sub 0 is 1. Why is that? Why is b sub 0 1? Let's prove that. Well, let g of z, remember, is z over e to the z minus 1. If I expand it out like this, b sub 0 plus b sub 1c plus dot dot dot, you notice, right? What is b sub 0? Look at the right-hand side. What is b sub 0? B sub 0 is exactly g of 0. In other words, if I plug in 0 for z, this term is going to get dropped out. This whole series is going to drop out because they all involve z. So the only thing left is b sub 0. So in other words, b sub 0 is really g of 0. But wait a minute, I cannot evaluate g of 0 because g of 0 is not defined. But I can take the limit. So that's the same as taking the limit of z over e to z minus 1 as z goes to 0. Now, you plug it in, you say, wait a minute, this is 0 on top, 0 on the bottom. 0 over 0, classic case for L'Hopital's rule. Remember what L'Hopital's rule says. If you're taking the limit as z going to something, that you're going to evaluate 0 over 0, you can consider differentiating the top individually and then differentiate the bottom separately, right? So you differentiate z, you're going to get 1. You differentiate e to the z minus 1, you're going to get e to the z. Now I have 1 over e to the z. Can I take the limit? Yes, you can, because now if you plug in z equal to 0, all you have is 1 over e to the 0, which is 1 over 1 or 1. So b sub 0 as a limit is 1. So that's how you prove b sub 0 is actually 1. Okay, second fact. Let's first ignore k equal to 1 for a minute. We'll come back to k equal to 1. Suppose starting k equal to 2, 3, 4, and so on. This recursion must hold, right? The sum of k chooses m, b sub m, where m runs from 0 to k minus 1, is 0. So this is going to be the fundamental recursion that we're going to use to evaluate these algorithmically. Why is that? Let's prove that. To prove this, let us begin by recalling if I were to multiply two infinite series. How do I do that? Imagine the first infinite series indexed by I, let's call it a sub I, and then the second infinite series indexed by j, let's call it b sub j. To multiply these two series, right, this is called the Cauchy's rule, which is the infinite series of k running from k equals 0 to infinity, and then inside each k, you're going to take the sum of m equals 0 to k, right, a sub m, b sub k minus m. Right? So let's use this rule to figure out what these are. Remember, let's start with z over e to z minus 1 is equal to this infinite series. If I were to multiply e to z minus 1 across, then I'm going to get z on this side, right? So z is going to be by itself. This is going to be e to z minus 1 times this series. Let me go and swap location, right? Let's put this b series in front. B series in front, e to the z. Well, we know how to do e to z, right? E to z is well known. Z to the L over L factorial. L runs from 0 to infinity. But I cannot have it run from L equal to 0 to infinity because I need to subtract 1. So when you subtract 1, this series, the first term will drop. So that forces this series to start from L equal to 1 instead of 0. Well, but that's no good because I cannot apply this rule here. I cannot apply the Cauchy rule because I need them both to start at 0. This guy starts at 1. What do you do? That's easy. Just do a change of variable, right? Let j equal to L minus 1. So when L starts at 1, j starts at 0. So if j is L minus 1, L must be j plus 1. So everywhere I see L, I replace it with j plus 1. So this is j plus 1 factorial, z to j plus 1. So now I'm back to this, both starting at 0, so I can apply this rule. Let's call this a sub I, b sub j. Plug it in. What is that? That's going to be a sub m, b sub m over m factorial, z to the m. What's b sub k minus m? 1 over k minus m plus 1 factorial, z to the k minus m plus 1. Multiply these together. B sub m, m factorial, k minus m plus 1 at the bottom. Instead of writing k minus m plus 1, I'm going to write it k plus 1 minus m factorial, right? And then here z to the m times z to the k minus m plus 1. The minus m and the plus m cancel. All you have is z to the k plus 1. Okay, so now I have it up to here. Now, at this point, I'm going to do a trick, right? I'm going to take this summand, so term by term, I'm going to take this summand. I'm going to multiply k plus 1 factorial, and then I'm going to divide by k plus 1 factorial, right? You agree. K starts from 0, right? So k plus 1 starts from 1. So all these are legit. This is perfectly okay, right? This is just multiplied by 1. But now, why did I do that? Well, because this guy here is exactly in combinatorial notation. This is exactly k plus 1 chooses m. That's exactly the formula k plus 1 chooses m. Whereas now this is b sub m, stays the same, and then multiply by z to the k plus 1 over k plus 1 factorial. Okay, so now I have up to this point. Now, from this expression, suppose I'm going to, I don't like this k plus 1 business, right? So let's replace it. Let's replace k with k minus 1 instead, in the inner sum. So take this inner sum, k replace k with k minus 1, so this k plus 1 becomes k, and so on, right? So this is become just z equals to the infinite series of k running from 1 to infinity of the inner sum of m running from m equals 0 to k minus 1, k chooses m, b sub m, z to the k over k factorial, right? Just make it look a little nicer. Now, you look at this and you say, what happens when k equals to 1? If you plug in this formula, right, when k is equal to 1, right, what you have is actually, what? B sub 0, right? Because remember, when k is equal to 1, you only sum to k minus 1, so you sum to 0. So in other words, just the m equals 0 time. What's 1 chooses 0? 1. B sub 1, which is 1. Right? We already established that. Z to the 1 over 1 factorial is z. So in other words, when k is equal to 1, this guy is just z. Oh, okay. So this infinite series is just z plus the infinite series from k running from 2 to infinity of this whole thing. Now you look at this and you say, hey, wait a minute. If I subtract z from both sides, don't I get 0 on this side? Yeah. Right? If you subtract z, you're going to get 0 equal to the series. Now, an infinite series equal to 0 is very tricky because depending on what value of z, you don't know what value of z that will make this 0. But you know what? We're not going to get into solving an infinite degree polynomial, right? All you need to know is, hey, you know what? If the coefficient was 0, then that would guarantee the whole thing is going to wipe out, right? It's going to be 0. So if I subtract 0 from both sides, I get 0 equal to the series. If this square bracket, the coefficient of z to the k, think about this, right? Because look at this inner sum. The inner sum depends on m. Z to the k over k factor has nothing to do with m. So I can just factor out like this. So if I can make this whole square bracket equal to 0, yeah, it's a sufficient condition that will make it 0, and that's exactly how you prove it. So in other words, this inner sum m equals 0 to k minus 1, if k chooses m, b sub m equals 0 for all k bigger than 1, that will do it, right? All right, so we dealt with k equals 0, we dealt with k greater than 1. What happens when k equals to 1? Let's work it out. What is b sub 1? Well, b sub 1 is negative a half, turns out. Why is that? Well, let's look at this. By the way, right, we know that because looking at this, right, we already know b sub 1 is negative half, right? So just looking at this, we know b sub 1 is that, but here's the proof of it. Starting with g of z equal to z over e to z minus 1, right? If you expand it out like this, b sub 0 plus b sub 1c plus this series, the rest of the series. Now, how do I isolate b1? That's difficult. Well, instead of thinking of g, what if you think g prime? Because when you take the derivative, right, this constant will drop out. This b1c goes to b1. Perfect. Right, so you're going to get b1 plus a bunch of stuff in terms of z. So all of these in terms of z, if I set them 0, then I have isolated b1. So in other words, b1 is actually g prime of 0. But wait a minute. What is g prime of 0, right? G prime of 0, you take the derivative. Remember, you cannot evaluate any derivatives at 0. So you have to take the limit instead. So this is the same as a limit of the derivative of the first derivative of z over e to the z minus 1. This is straightforward first year calculus. You differentiate this, you're going to get this, right? So it's the same as taking the limit z equals 0 of this guy. But wait a minute, I have a problem here. If you plug in z equal to 0, you notice something. This is 1 times negative 1 is now minus 1. Minus 1 plus 1 is 0. The bottom, right? This is 1 minus 2 plus 1. That's also 0. So I have 0 over 0. So I cannot just let z equal to 0 like that and by plugging it in. This is 0 over 0. So what do? You apply the L'Hopital's rule. You apply the L'Hopital's rule for the first time. You differentiate the top, you're going to get ze to the z. You differentiate the bottom, you're going to get 2e to the 2z minus 2e to the z. Now can I take the limit? Oh, don't forget this negative sign goes outside, right? So there's this negative sign here, this negative sign that goes outside. So can I now plug in z equals 0? Well, unfortunately, no, because if you do that, you're still going to get 0 over 0. Well, that's no good. So we have to apply L'Hopital's rule again. That's why you apply L'Hopital's rule twice. You do it again, what do you get now? You differentiate the top, you can get z plus 1 times e to the z. Differentiate the bottom, you're going to get 4e to the 2z minus 2e to the z. Can I now plug in 0? Yes, because now if I plug in 0 here, the top is just going to get 1. The bottom is going to get 4 minus 2 or 2. So don't forget the negative, so there's negative a half. So there you go. That proves that b sub 1 is actually negative a half. Okay? All right, so we now have 3 out of 4 properties. What's the fourth one? The fourth property is we need to prove that all the odd terms starting from 3 are 0, right? Remember, because looking at this, right, you notice that all these things are 0, right? So why is that? Why is that 0? How do you prove that? So basically, starting from 3, right, b3, b5, b7, all of these are 0. It's the same as saying b sub 2k plus 1 is 0 for all k greater than 0. I need to prove this. It is true. Now, how do you prove something like that? First, you need to consider the function, this function, x over e to x minus 1 plus x over 2. But before we do that, why would we do that? Let's start from the beginning. Remember, z over e to z minus 1 is b sub 0 plus b1z plus this infinite series, right? If I were to move b1z to the left, I'm gonna be left behind just b sub 0 plus this series. So consider h of z, a function h of z, as z over e to z minus 1 minus b sub 1z, right? Because I'm moving this b sub 1z to the left. Consider that, okay? If I move the b sub 1z to the left, all I have left with is just b sub 0 plus this infinite series. So in other words, h of z is b sub 0 plus this infinite series. Okay. Now, instead of working with complex number z, let's go and work with real number x as an input instead. So for all real number x, I want to consider what happens to h of x. I want to understand the shape of h of x. It turns out it's symmetric. Now, you could have graphed this and see that it's symmetric, but a graph is not a proof, right? So we need to work out the math to show exactly that it is symmetric. How do you do that? Let's consider h of x minus h of minus x. And I'm going to show this is 0. Because remember, if this is 0, right, then h of x becomes h of minus x. That means h must be an even function, right? So, but let's work it out. What is h of x minus h of minus x? Plug it in. X over e to x minus 1 plus x over 2. Right? That's how it's defined. Why plus x over 2? Because b1 is negative a half, right? So negative, it become a plus. So this is actually plus a half of x. Okay? All right, so h of x equal to this guy. What about h of minus x? You plug it in. Everywhere you see x, you put in negative x. You're going to get this. Minus negative x over e to the minus x plus minus 1. Don't forget, minus or minus give me a plus x over 2. X over 2 plus x over 2 is x. So this is x plus x over e to the x minus 1. Minus give me a plus x over e to the minus x minus 1. I can factor x out. So this is the same as x times 1 plus 1 over e to the x minus 1 plus 1 over e to the minus x minus 1. Right, continue. What is this? Look, let's focus on inside this parenthesis. What exactly does it equal to? Well, just find a common denominator, which of course is e to x minus 1 times e to the minus x minus 1. Right, the top equal to this. If you multiply this out, right, multiplying these out is 2 e to the x minus 1 times e to the minus x minus 1 is 2 minus e to x minus e to the minus x. Plug it in here. And then plus e to the minus x minus 1 plus e to the x minus 1. hey, something's funny happening, right? You see this minus e to the minus x and plus e to the minus x, they cancel. That becomes 0. Then you got this 2 minus e to the x and plus e to the x, they also cancel to 0. And then you got 2 minus 1, hey, that's also 0. So in other words, the top is 0, that means everything is 0. So we have now proved h of x minus h of minus x is 0. What does that mean? That means h of x must be h of minus x for all x. Now, what do you know about whenever h of x equal to h of minus x? That means it's an even function, right? So h must be an even function. That's a definition of an even function. Right? Okay, but wait, what is h though? But h is equal to this series. It's b sub 0 plus this infinite series. When can an infinite series be even? Right? If an infinite series is even, we do know one thing that cannot happen, which is k cannot have odd indices. Because if k has odd indices, you will never get this. So the only way for this to hold is if all the odd indices drop out. All odd indices is 0, and that proves b sub 2k plus 1 is 0 for all k equal to n. So meaning starting from 3, right? Starting from 3, b sub 3, b sub 5, b sub 7, and so on. All the odd indices starting from 3 must be 0. Okay, we have now proved that, right? That's the important property. All right, so with all these different properties that we have just shown, we now know, let's start building up the formula. You can now literally evaluate things, right? So how do you evaluate the values? Well, you evaluate them by going through this iteration. First, we don't need to worry about the first two cases, right? When k equals 0, we already established b sub 0 is 1. We already proved that. Similarly, when k is equal to 1, we don't need to do anything because we already proved b sub 1 is negative half. So those are done. The first two cases are done. Now, but this formula, remember, is only valid starting from k equal to 2, right? So that's why I need to calculate the first two cases separately. So when k equal to 2, plug it in. When k equal to 2, this formula kicks in, is valid. What is that? That's b sub 0 plus 3b1 plus 3b2 equal to 0. But I know b sub 0 is 1. I know b sub 1, negative half. So you can solve for b sub 2. What's b sub 2? Positive 1/6. Right? When k equal to 3, I don't need to do anything because I know it's 0. When k equal to 5, I don't need to do anything. I know it's 0 because I already shown in the previous theorem all the odd indices starting from 3, right, is going to b sub k is going to be 0. So you need to do the even. What about 4? 4 is going to be b sub 0 plus 5b1 plus 10b2 plus 10b3 plus 5b4. You can ignore this one because that's 0, right? So, and you know the rest of these. So you solve for b sub 4 is negative 130. And then b sub 6, positive 1 over 42, and so on. Okay? So using these theorem, we can now generate a system of equations, and then you can solve these. Okay? Don't quote me on this, but I believe there are a lot of, if you Google, right, so don't quote me on this, if you Google, there are lots of algorithms out there that actually, there are lots of programs out there that allows you to calculate this. I believe I actually look at the Python version, so you can actually calculate these things using an algorithm, which is based on this concept here. Right? So in the real world, right, if you want to know what all the b's are, you can actually do that. You can just evaluate using an algorithm, or you can write this on your own and evaluate. All right. Before we close out this series, this video, right, I want to share with you. Let's go back to the Faulhaber problem. Remember the Faulhaber problem is to find a general formula for S of n k. All right, so Orosi wrote a paper. I show you the reference. Feel free to take a look at that. Go back to the beginning of the video and take a look at that. He gave a very elegant proof of a general formula. So what happens when you take 1 to the k plus 2 to the k plus da 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 plus n to the k, right? He gives out this formula. You can actually plug in this nice formula, and here's how he proved it. Here's how Orosi proved it. So first of all, let's ignore the case equal to 1. I call it the trivial case. Here's the reason why. I mean, technically it's not that trivial, but anyway, if you plug in k equal to 1 here, right, you just immediately get the well-known formula, right? So 1 plus 2 plus da 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 up to n is n times n plus 1 over 2. So this is formula. If you plug in, you just establish it. So let's focus on the more general case. All right. So now this is important. Okay. Let's introduce this little n. So let's start with the little n. Okay. Not the general n, not the capital N, but little n. So if k and little n are natural number fixed, with k greater than or equal to 2, right? Again, when you plug in k equal to 1, you can evaluate it, it's trivial. Consider all complex numbers c. Let's define this function, f of z, 1 plus e to the z plus e to 2z plus dot 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 plus e to nz, little nz, okay? Let's call this expression single star. Now, recall from the geometric sum formula, whenever you have any quantity, fixed quantity r, 1 plus r squared plus dot 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 plus r to the n, it evaluates r to the n plus 1 minus 1 over r minus 1. Okay, you can prove this, right, very easily using literally elementary algebra. Now let us define capital N equal to little n plus 1. Okay, so instead of summing from 1, so capital N becomes little n plus 1. Now, what is f of z? F of z is going to be 1 plus e to the z, so think of this as r, 1 plus r, plus z to the z squared, or r squared, plus dot 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 e to the z n, or r to the n. This, according to this geometric sum formula, is e to the n plus 1 times z, minus 1 all over e to the z minus 1. But for simplicity, let's call little n plus 1 capital N. So this is e to the capital N z minus 1, all divided by e to the z minus 1. Let's call this expression double star. Right? So we have basically we now have two ways of representing f. Let's start with the left-hand side, the single star formula. Now, notice this function is written in terms of 1 plus e to the z plus e to 2z and so on, plus e to nz. This is infinitely differentiable because it involves e, right? So this is infinitely differentiable everywhere, right? So you can just differentiate it as many times as you like. And so what that means is I can build up a Maclaurin series of this guy over here. Well, let's start evaluating f of 0 as 1 plus dot 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 plus 1. How many times? Little n plus 1 times. So that's the same as s sub capital N, right? 0. Or if you like, is 1 plus s sub little n 0. Same thing. Okay? Now, let's take the derivative, right? So remember, f is this guy. When we differentiate, the first term drops out because it's a constant. So all you have is e to the z plus 2e to 2z and so on. So first derivative, e to z plus 2e to 2z plus dot 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 plus n e to nz. What happens if you evaluate this f prime at 0? Well, at 0, e to the 0 is always 1. So all of this will drop out. So all you have is f prime of 0 is 1 plus 2 plus dot 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 plus n, little n. So this is the same as s sub little n1. Let's take the second derivative, e to the z plus 2 squared e to 2z plus dot 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 plus n squared e to nz. Again, if you evaluate z equal to 0, f double prime of 0 must be 1 squared plus 2 squared plus dot 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 plus little n squared. That's the same as s sub little n2 in our notation. In general, the kth derivative, e to the z plus 2 to the k e to the 2z plus dot 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 plus n to the k e to the nz, evaluate z equal to 0, you're going to get 1 to the k plus 2 to the k plus dot 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 little n to the k. In our notation, that's s sub little n to the k. That's a little nk. So from this, what that means is, again, using just, this star expression, just using this expression here, you can now expand the Maclaurin series, right, in terms of this s sub little n. So f of z is nothing more than 1 plus s sub little n0 plus s of n1 over 1 factorial z plus s of n2 over 2 factorial z squared plus dot 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 up to s of nk over k factorial z to the k plus dot dot dot, right? Let's call this expression single pound because now I have expressed f, again, using only the left-hand side, the star. I have now expanded into this series form. All right, so that was the left-hand side, right? So that's star. Let's now work on the right-hand side. The right-hand side is double star, right? That's how you do that. So again, the right-hand side is a bit tricky because I have e to the nz minus 1 over e to the z minus 1. I'm going to split this into two fractions. That's why I need any z you like, any complex number z you like, except z equal to 0. Why? Because I need to divide by 0. So no 0 here. So as long as you stay away from 0, this is z over e to the z minus 1. Because by the way, z equals 0. This is not even defined, right? So you cannot have 0. So this, I can write it as z over e to the z minus 1 times the next another fraction, e to the nz minus 1 over z. Right? Now, let's work with the second fraction first. e to the something, right, is a well-known expansion. E to the w is 1 plus w squared over 2 factorial plus w cubed over 3 factorial plus dot, dot, dot. So I can write this out. So e to the nz minus 1 over z is the same as 1 over z times this infinite series. Everywhere you see w, you put in nz. So 1 plus nz plus n squared over 2 factorial z squared plus dot, dot, dot. Now I'm going to go to the k plus 1 term. In a minute, you will see why. So this is capital N to the k plus 1 over k plus 1 factorial z to the k plus 1 plus dot, dot, dot. Remember, I don't have to stop at k. I can stop at anywhere I want, right? I'm going to stop at k plus 1. Why is that? Because I need to divide by z out. Because when you divide by z, now what you're going to get, this 1 and this negative 1 will drop out. So all you have is n start with nz. So nz divided by z is it's going to be n. N squared over 2 factorial z squared divided by z is n squared over 2 factorial z. And then the next one will be n cubed over 3 factorial z squared. You notice, the power, the exponent of n is 2. The exponent of z is 1. The exponent of n is 3. The exponent of z is 2. So this is always 1 trailing. So in general, it's going to be capital N to the k plus 1 over k plus 1 factorial times z to the k. Right? So this is always 1 behind. The exponent of z is always 1 behind the exponent of n. Like that. And this is infinite series. Okay? Okay. So now I know the expansion of this guy, which is this. I also know the expansion of this. Why is that? Because that's the famous, right, the Euler, the Bernoulli numbers expansion. So z over e to z minus 1, remember, is b sub 0 plus b sub 1 z plus dot, 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 right? I want to express, ultimately I want to express f in terms of these Bernoulli numbers, right? And so you needed this. So now I have, again, going back here, right? So I got, to get this is the same as this infinite series times this infinite series. Okay, so what is that? Well, let's do that. So this infinite series times this infinite series. How do you multiply them out? It's not bad, right? Take this b sub 0 times n. So the first term is b sub 0 n. Done. Next term, I want to find everything that make up z to the first power. Well, what will make up z to the first power in this infinite series? Well, it's going to be b sub 0 times n squared over 2 factorial, right? That will get a z out of it. But also b1 times n. So I have b0 n squared over 2 factorial plus b1 times n. That will make up the coefficient of z. Okay, next, what about the coefficient of z squared? What would make up the coefficient of z squared? Well, there are 3 pieces. You can get b0 times n cubed over 3 factorial. That's 1 piece. But you can also get it out of b1 times n squared over 2 factorial, like this. I'm going to write b1 as b1 over 1 factorial, right? Like this. And then the last piece is going to be b2 over 2 factorial times n, right? So that will also make up. So these 3 pieces make up z squared. In general, here's a trick. In general, b0 will be the first term. So I'm going to write it as b0 over 0 factorial. Remember, 0 factorial is 1 times n to the k plus 1 over k plus 1 factorial. Next piece will be b1 over 1 factorial n to the k over k factorial. The one after that will be b2 over 2 factorial n to the k minus 1 over k minus 1 factorial. You're beginning to see the pattern. You see this, but look at the denominator here. This is 0 factorial, 1 factorial, 2 factorial, all the way in general to k factorial. This guy, on the other hand, over here, is going to be k plus 1 factorial, k minus 1 factorial, all the way to 1 factorial, right? And then the power is going to n to the k plus 1, n to the k minus 1, all the way to n to the 1. So there's a pattern here, right? So in a minute, we'll see where this pattern is, why this pattern is important. So all of this multiplied by z to the k, and plus dot, 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 because of the infinite series. There are infinitely many terms after that, but this is the general term, right? Let's call this expression double pound expression. Okay, so now I have a single pound expression. That's one way of expressing an infinite Maclaurin series of f. And now I also have a double pound. There's another way, another Maclaurin's, right, expansion of this guy. But they're the same. So I can equate the two equal to 0. I'm sorry, equate the two together, not equal to 0. Equate the two expressions together, right? And consider what happens when starting with k equal to 2. In general, I have s sub n k over k factorial. So that came from this guy here, right? So that's pound, this guy. In general, that must equal to this series, which is, not series, this sum, which is this guy, right? The coefficient. So these two coefficients must equal because they're both representing z to the k, right? Let's ignore b0 and b1, right? Because those we already know, so we don't need to worry about it. We just need to worry about the general case. So starting with k equal to 2. So starting k equal to 2, these two must be equal. So I want to solve what is S of n k. Remember, that's my goal. I want to find the general formula for S of n k. Well, let's solve for that. To get S of n k is easy, right? Just multiply k factorial to both sides. Now, but wait a minute. Instead of writing k factorial, I'm going to do something interesting. I'm going to do k plus 1 factorial over k plus 1. Now, you agree with me. K plus 1 factorial is k plus 1 times k factorial. But k plus 1 cancel. So this is just a fancy way of saying k factorial, right? Now, why did I do that? Because you see this 1 over k plus 1. Let's take them outside, right? Let's take this all the way outside. So 1 over k plus 1. Now, what about this k plus 1 factorial? I'm going to distribute it inside term by term. When I do that, the first term, I'm going to get k plus 1 factorial over k plus 1 factorial, b sub 0, n to the k plus 1, like this. What about second term? It's going to be k plus 1 factorial over 1 factorial, k factorial, and then b sub 1, n to the k, plus dot, dot, dot. The last term. What's the last term? Last term is going to be k plus 1 factorial over k factorial 1 factorial times b sub k times n. Now, why did I write it like that? Remember earlier I showed you there's a pattern, and there is. Look at the pattern. Look at this pattern. K plus 1 factorial over k plus 1 factorial. K plus 1 factorial over 1 factorial k factorial. And so on. This is the same thing as k plus 1 factorial over j factorial times k plus 1 minus j factorial, right? This is the same thing. So you're going to run j from 0 all the way to k. And that's exactly, but this formula is exactly, in combinatorial notation, is exactly k plus 1 chooses j. So in other words, I can now write this as 1 over k plus 1 of the sum of k plus 1 chooses j, b sub j, capital N to the k plus 1 minus j, where j runs from 0 to k. Okay? Now, at this point, right, we have it up to little n, but what happened is I wanted to write it as capital N, but capital N is little n plus 1, right? So let's consider what happens to S of capital N. Capital S of n, capital N, let's write it now, is the same as S sub little n plus 1 k. But S of little n plus 1 k is the same as S of n k plus capital N to the k, right? Because the next one will be n plus 1 to the k. So capital N k, right? Now, I'm going to write this follow. But S of n k, we have already established is equal to this guy. So that's just replace it in like this. Now, what about capital NK? I'm going to write it as follow. You see this capital NK, I'm going to write it as k plus 1 over k plus 1 times n capital NK, n to the k. But on the top, k plus 1 is the same as k plus 1 chooses 1 in combinatorial notation. So I'm going to deliberately write them like this. Right? Again, pause the video if you don't see why, right? So again, capital N to the k is the same as 1 times capital N to the k. 1 is the same as k plus 1 over k plus 1. In the top, k plus 1 is the same as k plus 1 chooses 1. So I've actually compressed multiple lines here into one, right? But I'm running out of space, so you can see why. So there you have it, right? So now, what about the rest? Well, let's break them up. You see this guy j runs from 0, right, to k. Let's break out 0 and 1. So when j is equal to 0, this is k plus 1 chooses 0, b sub 0, n to the k plus 1. When j is equal to 1, this is k plus 1 chooses 1 times b sub 1 times n to the k plus 1 minus j. But when j is equal to 1, this is the same as capital N to the k. But wait a minute, is that the same as capital N to the k here as well? Yeah, so I need to combine them. So in other words, I can combine this when j equal to 1 here with this term into 1. That's become b sub 1 plus 1, all times n to the k. So k plus 1 chooses 1 times b sub 1 plus 1 times n to the k, like this. And then the rest, starting j equal to 2 all the way to k, is the same. But now wait a second. What is this b sub 1 plus 1? Let's think about this. Remember b sub 1 we proved is negative a half. Right? So if b sub 1 is negative a half, what's negative b sub 1? Is positive a half. What's positive a half? Is negative a half plus 1. But what's negative a half plus 1 is b1 plus 1. So in other words, minus b1 is actually equal to b1 plus 1. So whenever I see b1 plus 1, I'm going to replace it with minus b1. So here we are. I got b1 plus 1. I'm going to replace it with minus b1. Right? From here. I'm going to replace it like that. And then the rest. Now, Let's look at these first two terms. I can combine them into a single one by taking the sum of j equals 0 to 1, minus 1 to the j, k plus 1 chooses j, b sub j, n to the k plus 1 minus j. Now you might say, wait, how do you get these two into this alternating? Look at what happened when j equals 0. Minus 1 to the 0 is positive 1. So it's just the same as this guy. When j is equal to 1, minus 1 to the 1 is minus 1. So this is just exactly that. So these two combine into this sum. Okay. Now what about the rest? The rest running from j equal to 2 to k. Here's what I'm going to do. I'm going to split out the even and odd indices. All right. So first, let's focus on the even index. All the even indices, I'm going to write them like this. This is a fancy way of saying even index when j is divisible by 2. This is a fancy way of saying, j is even. So here's the even series. So all the even indices, I'm going to put in this sum. What happens to the rest? Well, as the odd index. The odd indices is starting with 3, right? Because here's starting with j equal to 2. So here's starting j equal to 3. Whenever all the odd indices, right? This is a fancy way of saying that is when j is not divisible by 2, right? So whenever j is not divisible by 2, all the odd indices, I'm going to lump them together like this. But wait, we proved that starting with 3, b3, b5, b7, and so on, all these are 0. So wait, in other words, this whole sum is a 0. That's right. This whole sum is a 0, right? Because odd indices add up to 0. They're all 0. But wait, this is plus 0. Plus 0, can I write it as minus 0? Absolutely. Because plus 0 and minus 0 is the same thing. Mathematically, they're equivalent. Then this is important. That's why it's so important to prove that the odd indices, b sub odd indices is always 0 for all starting from 3, 5, 7, and so on, right? Because now it allows me to do this. So I can now go and take the plus 0 to minus 0. But now looking at this, I say, hey, wait a minute. These two summands are exactly identical. Of course, they're split out from the same thing. The only thing different is the sign. When it's even, it's positive. When it's odd, it's negative. What do? Just replace it with minus 1 to the j. So in other words, I can just take these two sums and combine them back into 1 by just throwing in minus 1 to the j. Because when j is even, all you have is all these are positive, so it's just the first sum. When j is odd, technically all 0, but doesn't matter, right? Because you're just subtracting 1 to 0. So in other words, these two sums add up to exactly this sum. All right? But now you look at this summand, and you look at this summand, you say, hey, wait a minute, they're exactly the same. Yes, they are. And so we can just combine these two as well. So that's right. So instead of running from j equals 0 to 1 and then running from j from 2 to k, just combine them into a single one. So just run from j equals 0 to k of this expression. And that's the proof. That's Orosi's proof of this general formula. So he had now proof. Again, it's very elegant proof. It's very straightforward. There's a little bit of algebra here. You have to think through this a bit. But again, it's not that complicated. Okay, so that proves it. So, okay, so this is the end of this video, right? We have now introduced the Bernoulli numbers. So you now know the Bernoulli numbers. And we have some important properties that we look at all the Bernoulli numbers, right? For example, what we prove? We prove the b sub 0 is 1. We have proved that b sub 1 is negative half. We have proved that starting from b sub 3, all the odd indices, b sub 3, b sub 5, b sub 7, and so on, all the odd indices, the b's are 0, right? So that fits exactly this pattern here that we see. We now have established this. There's anyway, I really like Orosi's proof because it's very straightforward. It's very simple, very straightforward. It's basically just a lot of algebra work and careful accounting of all the positive and negative signs. But you can now, we have now established this. And using what we established, where is it? Using this situation, right? So using this as a recursion, you can actually build out all of these. So you can write an algorithm and figure out all the Bernoulli numbers. So, there you have it. So if you want to see one single formula dealing with 1 to the k plus 2 to the k plus dot 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 plus n to the k, here's how you do it. Anyway, I hope this is a useful video to you. And if you have any comments, write down in the comment section. I appreciate you watching this. Thank you. Bye-bye.